Now that we have a basic understanding of the state of water and the challenges of managing water and our regulatory framework in the United States for stormwater and water pollution control management, let's turn our attention to the design process. This is a bit of an overview of where we're headed in this class, and I provide this now to give you a sense of the outcome at the end of this series of lectures and exercises, so that you'll see what you'll have the skills to understand and do. This is Chapter 1, Lecture 6, Framing and Design to Inform Decisions and Resiliency. I'm Dr. Marty Matlock. Remember that everything is connected. Our ecosystem services upon which all civilization depend come from the land, from water, and they provide the constituents of well-being upon which we all benefit. Everything is changing. We talked in Lecture 1 about the rate of change, and we're all in this together. So today's lecture really is about the we're all in this together part, about how we make decisions, who makes decisions, and why we make decisions about how we manage common resources like water. Remember, we know what we're trying to work towards, improvement of the Sustainable Development Goals. Nassim Nicholas Taleb has become pretty famous lately because of his black swan characterization, but in his book, Anti-Fragile, he talks about resiliency and fragility. Some things benefit from shocks. They thrive and grow when exposed to volatility, randomness, disorder, and stressors, and love, adventure, risk, and uncertainty. Anti-fragile is beyond resiliency or robustness. The resilient resists shocks and stays the same. The anti-fragile gets better. So Taleb is arguing that anti-fragile is a better design criteria than just resilient. Resilient is being able to stand back up when you get knocked down. Anti-fragile is getting stronger every time you get knocked down. Anti-fragility makes us understand fragility better. Just as we cannot improve health without reducing disease or increase wealth without first decreasing losses or poverty, anti-fragility and fragility are degrees on a spectrum. Some become anti-fragile at the expense of others by getting the upside or gains from volatility, variations, and disorders, and exposing others to the downsides, the risk and loss or losses and harms from those events. And such anti-fragility at the cost of fragility of others is hidden by government policy in the name of economic stability. It is a way to perpetuate poverty and to perpetuate risk amongst usually ethnically minority groups. The chief ethical rule is the following: thou shalt not have anti-fragility at the expense of the fragility of others. This is a good engineering design principle, not just for people, but for systems. Don't make your system more resilient at the expense of other systems. Don't prevent flooding in your reach of the watershed and cause flooding downstream or upstream. Danny Kahneman, who's a social psychologist, won a Nobel Prize in Economics, 2003, I believe, for thinking fast and slow, argues that the way we understand things really is risk-based, and we are fundamentally risk-averse. So as engineers, as we're trying to talk to to the clients, the people who will build the things we're designing, because we're generally not the builders, we're not the financiers, as we're trying to convince them of the value of the thing, it's important to frame risk properly. Because we construct mental models of how the world works. As engineers, we're really good at this, but everybody does. Most people's mental models are just horribly wrong. They're subject to bias because, first of all, we have spurious correlation. We think things are related when they're absolutely not. We have changing conditions in relationships, so even the relationships and the correlations that we understood from past experiences may not apply anymore. This is particularly true with hydrology, climate change, and rainfall frequency and intensity return periods. When we have a sense of control over something, that provides a sense of good bias. That makes us comfortable. A sense of control, we can make it better, will motivate us to act. A sense of dread is a bad bias, and it tends to motivate inaction, interestingly enough, in spite of modern environmental movements claiming that the whole world is going to burn, thinking that that's the way you're going to motivate behavior. It does not motivate action amongst most people. In fact, that sense of dread often motivates inaction. What you see is all there is. Wasiati. Our disciplines give us the language to understand the world and to build models, that is, heuristics, to address problems, design systems, and create the future. But we see the world through our discipline eyes. We do not see the world as sort of above the discipline fray. So we're limited by what we see and, frankly, the language we speak, the words we use. So we have to expand our gaze, and that means expand our language so that we can see the world more completely, understand the change that we desire more effectively, and finally drive that change we need to be successful. That is, we have to convince people to build the things we design. George Box said, all models are wrong, some models are useful. So we have to expand our language to build new models of understanding so we can more effectively address complex problems, identify effective solutions, and create more responsive systems. That interdisciplinary thinking allows us to build more useful models. And so even as engineers taking a course in hydrology, it's important to look beyond engineering hydrology to other disciplines to think about how we frame questions and how our problem solving could be improved. That's why we tell stories. We want to make more sustainable decisions. Stories, like mental models, allow us to put our experiences into context and change our behavior or motivate new actions. Stories are narratives that have linearity to them. They have beginnings, middles, and ends. As designers, we need to have beginnings, middles, and ends in our designs. So that what makes a story effective? It has to be credible. It has to speak truth. We have to convince people of the truth of our designs. Now, as professional engineers, we have a certain amount of credibility that comes with the profession. But we still are in situations where we're going to be convincing people of things they've not experienced before, the probability of extreme events that they don't frankly believe. So the story must be based in and honest about facts. Remember Maya Angelou saying facts can get in the way of truth. So we have to be honest about our facts as we move towards truth. The story must interest people. So it has to represent the facts in a way that people can relate to, understand, and care about. So that means when you're developing a design, a hydrologic design for stormwater management, for low-impact development, for ecosystem services, regardless of what you're developing the design for, keep this all about people, because people are what matter. They pay for this. The story must address relationships, build trust, and reinforce norms. Connect it to your local community. So I'm going to give you an example of just a story. Rethinking Urban Hydrology in Conway, Arkansas. The Community Design Center and the Resiliency Center, was the Office for Sustainability at the time, were contracted by ANRC, Arkansas Natural Resource Commission, through EPA, through the EPA subsection 319 of the Clean Water Act program, to develop a non-point source 9-element management plan for the city of Conway, Arkansas. The city had experienced a number of problems and had a number of challenges, so we developed a framework to address these challenges. So I'm telling you this story because I want you to see the sorts of things that we can do as hydrologists and how we can work with architects and designers to better explain our situation. So we start with the human impact from climate change, flooding. Conway, Arkansas, as you can see on the left, is flooding frequently. That's not an old 1940s picture, even though it's black and white. Look at the models of the cars. They're relatively contemporary. Those floods are the 21st century floods. 2 to 3 feet of water in Main Street that you can see to your right or on Broadway. So we had to rethink how water moves in this system, through this urban system. So if we look at it, we decided to shift the exploration of the plan from the watershed to downtown where ecological and economic interests intersect, because that's where decisions are made. More cities are tasking urban infrastructure with regeneration of these really declining urban ecosystem services to support livable communities. So that means we have to use hydrology as a way to design more than just watershed or water conveyance, because hydrology now becomes a vehicle to create greenways, a vehicle to create trails, a greenway to create boulevards with trees, with vegetation in our urban cities. So we had to move to what architects call soft engineering. It's just ecological engineering. This is where this class, as we touch on these issues, this is where we have an eco-hydrological emphasis. Now, there are 17 ecosystem services, typically framed as atmospheric regulation, climate regulation, disturbance regulation, water supply, erosion control and sediment, soil fermentation, nutrient cycling, waste treatment, pollination, species control, refugia and habitat, food production, raw material production, genetic resources, recreation, and cultural enrichment. Of those 17 ecosystem services, 11 of them are directly related to what hydrologists design. By the way, it's just coincidence that there are also 17 Sustainable Development Goals. So working at Conway, you can see the existing landscape to the left in a downtown brownfield. A brownfield is an old industrial site that has been abandoned. It's an existing scrapyard on Markham Street. And then reimagining that as a public goods ecosystem services providing hydrologic feature. So the first thing we had to do is look at the context of this system, frame the problem. And we're going to spend a lot of time in the coming weeks learning how to do this sort of framing, starting with characterizing the watershed. So this is Lake Conway Point Removed Watershed. It's a 1,144 square mile area. It's a 8-digit hydrologic unit code. You can see the 8-digit code there. Population was 131,391 people in 2010. You see that Conway and the Little Creek, Palarm Creek sub-watersheds are down at the bottom southeast corner or southeast edge of this watershed. It includes a number of cities: Conway, Mayflower, Valonia, Morrilton, Pottsville, Russellville. So it's a fairly big watershed. Arkansas River anchors it to the south. Then we had to create a language of low-impact development to explain to the community how, and the community designers, the engineers, what sorts of things we would look at. And so working with our Community Design Center, we looked at sort of a language of problem solving, then a language of systems. So we looked at lake restoration, green street and parks, parking gardens, urban eco farms, city greenways, and conservation development as sort of problem frameworks. Then we looked at condition frameworks or context frameworks for the city in order to deal with water flow through the city. Are the streets pixelated? Many are in our region. Are they nested? Some are. Are they clustered with sort of around water bodies or connected? And we have all four of these fabrics of streets, of street grids within the city of Conway. We had to visualize design elements, telling the story. What can you do? Well, you can control flow, you can detain water, you can retain water, you can filter water, and you can infilter water, and you can treat water with technologies, hydrologic technologies, in these cases, both conventional and low-impact development technologies on the land. We had to give them a language of design elements. And then we finally had to put the data in context. So ecoregions were the start. As hydrologists, we are always operating in an ecoregional context. The subwatersheds exist within ecoregions. Ecoregions are areas of homologous weather, climate, slope, geology, and ecophysiology, which is to say they look the same. So the Arkansas Valley Hills, scattered high ridges, Arkansas Valley Plains, Fuchs Mountains, those are the ecoregions that we're operating in. Now, Conway gets 51 inches of rain annually, 30% more than the national average. It's a wet region. Rain terrains and riparian landscapes are key here. Understanding that is important because also understanding what the larger landscape impacts will be from the rains and what happens when those rains become more intense. We had to contextualize the urban impacts. So we had to identify sources of problems within this watershed. Since the first hour of urban stormwater runoff can have a pollution index greater than raw sewage in some cases, because depending on how long it's been since it's rained, stuff just accumulates on the ground. Dog poop, cow poop, bird poop, lots of poop, and other things, oil and grease from cars, dust that's been blown in. The first rains flush all that off, and that is incredibly dirty water. So understand, and it all in this system, it all drains down to Lake Conway. So we have Little Creek, Stone Dam Creek. So we have Peri-urban Creek. We have three major creek systems here. We have Hendrix College, UCA campus, County Fairgrounds, a couple of other downtown Conway, a couple of other major elements, some industries in this sub-watershed. Non-point source pollution can be natural or human-made, synthetic fertilizers, herbicides, etc. The whole spectrum of these had to be analyzed. We had to evaluate change. What is now, what used to be, what will be. It's more than a third of the city's built environment is projected to exist by 2030. Has not yet been built. That is, it's going to increase by 30% more in the next 10 years, 15 when we did this work. Now's the time to implement programs to manage for that change. So they're going to grow to 88,000 by 2030, 10 years from now. That's an additional 25,000 people from 5 years ago. That's 10,000 new dwellings, more than 3,400 acres of dwellings. You see the grids that represent 10,000 new housing starts have to be located within the current grid framework you see for housing in neighborhoods and residential and industrial areas in this watershed. So then we had to give language to the problems, framing solutions. Starts with the problemscape. So we mapped the myriad manifestations of non-point source pollution, their expression in stream dysfunction across sub-watersheds, forms and starting points for urban watershed framing plan. When human activities indicated that, while human activities indicated are not defective, they're not that we're doing bad things, they're essential to our economies, they can have negative externalities because they're generally unregulated, and so the public pays for the impacts. A holistic approach to watershed management is within easy grasp. So the problemscape we developed has 5 riparian corridors. We identified and mapped the riparian corridors across the different systems from Gold Creek, Stone Dam Creek, Stone Dam Creek tributary, Little Creek, and Little Creek tributary. This gives us a landscape to analyze. Stone Dam Creek problemscape. We have unprotected headwaters, loss of vegetation in the riparian zones, unprotected vegetation in the riparian edge, and we have chemical inputs from runoff from agricultural and residential area. This is predominantly an agricultural watershed and residential watershed with a little urban or campus development at the upper end. Stone Dam Creek tributary is a little more, it's a fairly small and fairly linear watershed with unprotected headwaters, a lot of channelizing piping, industrial development in the mid-watershed with chemical inputs from agriculture, not especially nutrients and organic carbon at the bottom from agriculture. Little Creek problem shed had impervious paving along streams, which means a lot of additional runoff, a loss of riparian vegetation, a lot of chemical inputs, excess sedimentation within the lake. Finally, Little Creek, we have loss of floodplain by residential and agricultural encroachment, and it's going to get worse as we put 10,000 more houses in this watershed. Agricultural chemical inputs, again, nitrogen, phosphorus, potassium, and organic carbon, and livestock in the stream. And those livestock are brutal to the stream banks and stream bottoms and the vegetation. And then we had to provide a focus for action. So residential development, the clear cuts vegetation from the headwaters, elimination of riparian vegetation from pastures, gravel mining and erosion adjacent to the streams. Those are things we can start to identify as direct impacts. That was in Gold Creek. Now that means making decisions. So we developed a plan, a urban watershed framework plan, working with stakeholders. Cities are discrete, but nature is not. Nature doesn't care about our city boundaries. So the sort of transition from natural to human dominated is a fluid thing. So we use the language of design that we described earlier across the problemscape to try to help plug in elements of design to reduce the problems using good engineering hydrologic design. So the first concern was lake restoration. This is very much an ecological design, an eco-hydrologic design, because we had to deal with nutrients and sediment. We had to deal with flooding, and we had to deal with eutrophication in the reservoir. See how green it is? Now, fortunately, we did have intact riparian zones in the headwaters, which gave us a lot of strength and activities. So the choices give power to decision makers. So we can say if excessive sedimentation from contributing streams creates eutrophic zones in the lake's mouth, depriving of oxygen, then dredging and island creation is an option. So pulling that sediment up, creating deeper waters, and then creating lots of edges for the to amplify ecosystems and to break up water flow for more, so we settle out and slow down the flow of water so that the sediment doesn't make it to the middle of the channel. Putting vegetation on the edge to also filter out water. And then we can provide a number of other interventions like floating wetlands and other tools to also reduce nutrient loads. But the details always matter. So designing these things means quantifying their impacts and the risks and uncertainties. This is not just fancy gardening. These sorts of designs require competent and fairly complex calculation, simulation modeling, and scenario analyses with risk assessment. We also looked at green streets and parks in the urban downtown, looking at developing a green loop with a shaded shared street, green alleys, and neighborhood parks. You can see in the grid symbol to the left, and you can imagine that overlaid to the right. So with the green streets and parks, we have shared street types, which allow for much more urban pedestrian traffic, a new neighborhood downtown town square garden that's also a hydrologic retention and detention system, green street, another green street type on the boulevard, as well as green street alleys along the riparian zones. So the Green Street Park, that's the Markham Town Square, has a number of elements. Wetland Town Square, rain gardens, bioretention mats, green streets, which means infiltration streets, evapotranspiration tree bosques. That's an area where you have a lot of root mass from trees in order to pull water out from frequent low-intensity storms. A living bridge, it's a bridge with lots of plants on it, and multi-programmatic mounds, which have lots of things you can do on them. The mounds also are infiltration zones, and you could even put hard infrastructure under those mounds, like water collection systems. So to understand what the problem really is, looking at this system before you try to solve it is the key, because that gives us more language to solve the problem. Because now we can use this park as our flood retention system downtown, and it's not just a big empty lot in the middle of town, but it does serve to buffer extreme rainfall event flows and therefore protect downtown from flooding. So the problems, flooding, become solutions, parks. And those solutions expand ecosystem services for habitat, for nutrient cycling, for all sorts of, we have 17 ecosystem services we care about. The one that matters most is a sense of place from people. So the people's experience. So as we envision what the landscape does, and this is a landscape we as hydrologists are designing, we have to understand the interconnectedness, because everything's connected, of the landscape of the water all the way through the system, because the water that's in the water table is actually coming through, in many cases, the soil as interflow into the stream or the pond or the reservoir, and it's coming as it comes through that system, it's intersecting a number of guilds of animals and plants and insects, which are animals too. But so that's the way we have to think about these things. More than people live in the watershed and impact it, and it doesn't matter how much you try to restore a watershed if 50 cows decide to walk through it 3 times a day. Streamside buffer zones can reduce pollutants by as much as 95%. That means keeping the cows out. That just means a little fence. So visualize the possible. If farming practices exist that destroy streams, then fix it by putting off-stream watering system for cattle, provide flood harvesting ponds for irrigation, restore riparian edge, and create increased ecosystem services for both the landowner as well as the community. Peri-urban agriculture, which is agriculture on the urban edge, is a huge opportunity for enhancing ecosystem services. Solutions come from understanding the problem. That's the key. Understanding the problem gives us a sense of where we have opportunities. So the City Greenway Wetland Preserve provides a number of integrated activities for people to engage in. This is a fairly rural area, and people love it because of that, so we need to celebrate the rural nature of this particular area. You've already seen the Stormwater Regulations as part of your previous readings. Take a look at the City of Fayetteville Stormwater Regulations. Later in the class, we will talk about low-impact development options and design as we dig deeper. This concludes this lecture. Thank you.